Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we derived these 4 equations, simultaneous equations, right. If you look at these equations basically, so these equations we have got by putting the proper boundary conditions of a particular problem. In the last lecture we have seen. So, C1, C2, C3, C4 all are integration constants. Now, if you want to solve this type of say simultaneous equations, basically this is in mathematics it is called as eigenvalue problem, right, as you know. Anyway, so if you one of the trivial solution of this equation of these equations is C1 equal to C2 equal to C3 equal to C4 equal to 0, right, already we have seen in the last lecture. So, but that is a trivial solution and we are not looking for that, because what does it mean C1 to C4, if all integration constants are 0, that means there is no deflection or the no say displacement of the slender member or the beam or the column, right. So, that we are not looking for, that means the load is such that there is no deflection of the column, right, in the lateral direction. So, that we are not looking for at this moment. We want to find out the critical load for which the column really sways in the lateral direction. Okay. So, if I want to get the non-trivial solution for these simultaneous equations, so basically from equation 4 and 2, okay, we get C2 equal to C3 equal to 0, that we are getting. If you look at equation 4 and equation 2, we can say C2 and C3 are 0. Now, from equation 1 we can say C4 equal to minus C1, okay, quite simple. Now, from equation 3 what we can write, we can write C1 P by EI cos root over P by EI L equal to 0. Now, in place of C4 we are just putting minus C1 and we are getting this expression from equation 3, because C3 is 0, already we have seen that. Now, in this equation C1 cannot be 0, because if C1 becomes 0, then again we are getting the non-trivial trivial solution, right, all integration, all constants are 0, that we are not looking for, as I told you. So, if C1 is not equal to 0, then of course this part has to be 0. So, P by EI cos root over P by EI into L must be 0. So, if that is 0, then from this we can write cos root over P by EI into L equal to 0, and this can be further written as. Now, if you look at this, we are looking for the smallest possible load for which you are getting the instability, right. If you are talking about the P critical, that means that is the smallest possible load for which the instability occurs in the column, right. Now, if you look at this equation, you can have the solution like cos 2n minus 1 into pi by 2, right, that you know from mathematics, but that will give you the lowest possible load as well as the load for the higher modes, that we are not looking for. We are trying to find out the lowest possible load. So, if I want to find out the lowest possible load for which the instability occurs, then I can simply write cos root over p by ei, L is nothing but cos pi by 2. So, from this I can get it p equal to pi square by 4 ei by L square, okay, which can be expressed like this: p equal to c, some coefficient c, into ei by L square, where the coefficient c is nothing but pi square by 4. So, now this is basically your P critical. This is the lowest possible load for which the instability occurs for that kind of boundary condition. So, if your boundary conditions are changing, okay, if you are providing, or if you are considering different boundary conditions, that we will be seeing right now, okay, later on. If you change or alter your boundary conditions, then what will happen in the solution, okay. So, there we will see that if you change the boundary conditions, basically this ei by L square will be remaining same, that will be remaining there, but only this coefficient value will be getting changed. So, that we will see later on. But what I mean to say, this is your lowest possible load, okay, for which you are getting the instability for the boundary condition whatever we considered, okay. Now, once you are loading the column, gradually you are loading the column. Once your load is reaching this point, this magnitude, okay, c into this pi square by 4 into ei by L square, immediately the system will go to the instability, okay. Now at that position, okay, when you are looking for the instability, at that time your V, that is the deflection, okay, lateral deflection, is equal to C1, because C1 is already some, because C1 is not 0, and if C1 is not 0, then only we are getting this solution, right. So, C1 multiplied by, you can see from the original equation, cos pi by 2 x by L. Now, what does it mean? Now, from this equation it is very much clear that C1 can take any value, right. So, C1 can be any value, but for that C1, okay, for that C1 value your system will deflect, okay, but it will give you the stable configuration, right. And this kind of stability already you have seen, that is your neutral equilibrium. That means your body, if you recall in the previous lecture we discussed about 3 kinds of instability. One was the stable equilibrium, another one is the unstable equilibrium, another one is the neutral equilibrium. The neutral equilibrium is that the body was here, now I am moving this body from here to here, the body is still under equilibrium, right. It is not coming back to its original position, but it is still under equilibrium. That kind of situation happens here. So, whatever value of C1 you choose, your system will be under neutral equilibrium. That means, if you increase the load, if you are putting the load, okay, that will give you some deflection on the lateral direction, but still the column will be under equilibrium, okay, and that is called, that is the thing is neutral equilibrium, okay. So, now if you look at different boundary conditions, okay, as I told you, if you consider different boundary conditions, then how your solution will be altered. Now, you look at these figures, okay. So, we just looked at this part, okay, we considered this boundary condition, that means one end is clamped, another end is free, okay. At that time, if you want to find out the P critical, so the P critical, already we have seen that P critical is given by this, as I showed you in the board, that is coefficient C into ei by L square. So, that is this coefficient C will take the value pi square by 4, that already we have calculated or we will have derived by considering this kind of boundary conditions. Now, if you change the boundary condition, now you come to this kind of boundary condition. In this boundary condition, this end is hinged, not the clamp, that means not the fixed one. This end is also hinged. Okay? If you change the boundary conditions like that, then your coefficient C will take the value as pi square. That you can prove it, alright. Okay. Now, similarly, if you consider one end is clamped, another end is hinged, then your coefficient will take the value of 20.2. That also you can derive by putting different boundary conditions. You solve in a similar fashion or similar way, you will get it. We will take one numerical example with different boundary conditions, then you will see that these values will be coming. Okay. Now, if you change the boundary conditions like that, both ends are clamped, that means this end is fixed, this end is also fixed, then at that time your C is 4 pi square, right, 4 pi square. Now, if you look at this coefficient, this is 4 pi square and this is pi square by 4, right, this is pi square by 4 and this is 4 pi square. Now, what does it mean basically? Suppose your column is something like that, one end is free, another end is clamped. Instead of that, if you are using this kind of column where both the ends are fixed or the clamped, then basically you will be getting higher P critical. Okay? That means the column will carry more load without having the instability problem, right, that shows here, right, that shows here. So, if you change from A, B, if you change like that, if you change the boundary conditions like that, your carrying capacity of what I am saying, carrying capacity is nothing but without violating the instability. The carrying capacity of the column without showing the instability will be enhanced by changing the boundary conditions likewise. Okay. Now, with this I conclude this chapter. Now, we will take a few numerical problems and then you will understand that how we can find out the P critical for different kind of structures with different boundary conditions. Okay. The problem says the rigid strut AB is pivoted without friction at B and is stabilized by a spring of stiffness K which is unstretched when x equal to 0, find the critical value for a load P which is delivered by a rope. I will show the figure, it will be clear, passing through a guide O. Okay. So, if you see the figure, Okay, so this is the problem. The rigid strut AB, okay, is pivoted without friction at B, is stabilized by a spring of stiffness K. That means the spring is trying to prevent the lateral movement, okay, which is unstretched when x equal to 0. That means when x equal to 0, at that time the spring is unstretched, then the spring is not experiencing any deformation. But when the strut is, I mean, experiencing some lateral displacement, say x, then the spring is getting stretched. Okay. Find the critical value of a load P which is delivered by a rope. So, this orange line is your rope. Okay. So, we are pulling this end A through this rope which is passing through a guide O. Okay. So, this is some guide, some roller kind of thing through this rope is passing through. Okay. So, here actually the load is vertical and this is the inclined rope. Okay. Now, this is the problem. So, let us solve this problem by using our knowledge whatever we have gathered in this chapter. So, if you draw the free body diagram of your strut AB, the spring will be giving some force Kx, it will be trying to pull it back, and this is the load say P prime, because P load and the load through the rope will not be same, because you are having the inclined rope and which is passing through the guide and it is vertical. So, P and P prime will not be same. So, that is a P prime which is the tension applied through the rope, okay, and this angle is say theta, and this is say L as shown in the figure. So, this is your point A and point B, fine. This is the loading system, okay, externally applied loads on the strut AB. So, if you consider the moment equilibrium, then basically we can write Kx plus P prime sin theta, okay, P prime the component of P prime along the horizontal direction multiplied by L is equal to P prime cos theta into x. Very simple equation, because now you are quite familiar to this kind of say moment equilibrium equation or the force equilibrium equation, right. So, from this I can get the expression of P prime, that is Kxl by x cos theta minus L sin theta. Okay. Now, from geometry what I can get, from geometry if you look at, this is the angle theta, okay, this is x and this is twice L. So, from this I can get tan theta is equal to x by twice L, okay. This is coming from the geometry. You look at this geometry, okay. So, this is the rope, okay, this is your rope, fine. So, now if I put those the value of, now if I extract the value of sin theta and cos theta from that expression which is coming from the geometry, then what I can write, I can simply write now at O what is happening, this is the P prime and this is your P, okay. This angle is say theta, right. So, I can simply write, so this is our objective function, right, to find out the P critical. So, P is nothing but P prime cos theta as per definition, okay. So, here instead of P prime we can write Kxl by x cos theta minus L sin theta into cos theta. So, now if I eliminate theta by putting the geometric parameters x and L, then I can get from here simply kxl by x by 2, which gives me twice k. So, this is my critical value of P, for which the strata will be experiencing some amount of deflection x. Is it clear? Okay. Now, we will take another example. So, in this problem, basically this is the problem. Okay. So, there is a column or beam, whatever. Okay. If it is, so basically this is a kind of orientation, right? If it is, I mean both are your slender members, which will be carrying bending moment and shear force. Okay. Of course, as you know from already we have discussed this thing. So, beam is a horizontal member and column is a vertical member. Anyway, so this kind of boundary conditions we are considering, or we are considering this kind of end conditions, both ends are hinged in this problem, right. Already you have seen the solution for this, okay, that coefficient value C value already I have shown you in that table. Okay. Now, we are going to solve this problem. Let us see whether we are getting that solution or not. Okay. The EI is constant, okay. The length of the member is say L. Now, we need to find out the critical elastic compressive load, the P critical, okay, for a uniform flexible beam which is hinged at both ends. So, that is the problem. Okay. Now, we need to find out P critical, which is compressive in nature. Fine. So, we will start from this, that is our basic equation, V equal to C1 plus, if you go back to your previous class note, you will see that C2x plus C3 sin x by root over P by EI plus C4 cos x root over P by EI. Say this is my equation 1, right. So, this is our basic equation. By solving the differential equation, we will be getting 4 integration constants that already you have derived. So, if we take dv dx, then I can get simply C2 plus C3k cos kx, where k is nothing but root over P by EI. Instead of writing every time root over P by EI, okay, so we are writing k, okay. C3k into cos kx minus C4 k into sin kx, okay. We can find out d2x, d2v, dx2. For some purpose we are doing that. I will come to that point right now. That is C3 k square sin kx minus C4 k square cos kx, okay. So, as we know, MB, that is the bending moment, is given by EI d2v dx2. So, for that purpose actually we are calculating this. So, k square is nothing but P by EI, right. So, EI into k is nothing but your P, right. So, we can simply write minus C3p sin kx minus C4p cos kx, say equation 2. Okay. Now, what are the boundary conditions? Now, we have got two equations. One equation is giving me the deflection, okay, along the y direction. Y is the vertical direction, x is the horizontal direction. So, along y direction we have got the deflection, that which is v, and the bending moment we have got, that is given by the equation 2. Now, if you see the boundary conditions in that beam at x equal to 0 and at x equal to L, what are the things we can write? What are the boundary conditions? At x equal to 0 and x equal to L, your v is 0 because both ends are hinged. So, there cannot be any v, that is deflection. So, v is 0 for both the locations. Now, what about bending moment? Because both ends are hinged, so there cannot be any bending moment. So, mb is also 0. Fine. So, now if you put those boundary conditions in equation 1 and 2, if you put these boundary conditions in equation 1 and 2, you will be getting 4 equations, C1 plus C4 equal to 0, C1 plus C2 L plus C3 sin KL plus C4 cos KL equal to 0. So, this is my equation A, say, this is B minus C4 P equal to 0. So, equation C, and final equation is C3 P sin KL minus C4 P cos KL equal to 0. So, equation D. Now, if you solve these 4 simultaneous equations, so you will be getting the values of integration constants like that. So, your from C and A, from these two equations you can get C1 equal to minus C4 equal to 0. Okay. From D we can write minus C3P sin KL equal to 0. So, C3 and P both cannot be 0, right. C3 and P both cannot be 0, right. So, if you say these are not 0, then I can simply say sin KL equal to 0, which is nothing but sin n pi. I can write where n equal to 1, 2, 3 and so on. So, from this I can simply write KL equal to n pi, right. Now, what is K? K is nothing but root over P by EI into L equal to n pi. So, what I can write? From this we can write P equal to EI n square pi square by L square. I can write. Now, what we are looking for? We are looking for the lowest possible value, critical value, okay, for which your instability occurs. So, n should be 1 for that case. So, if I want to find out the minimum value, that is the smallest value, P is nothing but, say, P critical is n equal to 1. So, EI by L square into pi square. Okay. Now, if you look at this figure, okay, so this problem is like this. Okay, whatever problem we just solved, this problem is basically this problem. So, this problem, your coefficient C is pi square, right, we have proved it. Similarly, you can prove other two cases. by changing the boundary conditions and solving the basic equations. Okay? So, I will stop here today. In the next class, we will be continuing with some numerical problems on Castigliono's theorem. Okay? Thank you very much.